Today, we will be talking about kinematics 1D motion analysis. First, let's review on what we have learned last lesson. Displacement is the change in distance over a set period of time. In other words, delta x, change in x, is displacement which is gotten from the final position minus the initial position. Whereas distance is something else, which is total amount traveled instead of just the distance between the 2 points, initial and final. Now, what does this Greek triangle mean? This you will see a lot in kinematics, and it means change in delta. So when I say delta x, I mean change in x. And now let's talk about kinematics. So, first of all, what is kinematics? Kinematics is the study that talks about motion and the movement of objects. It focuses on velocity, acceleration, and displacement. So, what is velocity now? Velocity, as we recall, is basically just displacement over time. So, it would be the change in position over the change in time, which I will represent in delta t. Change in time. And this is very useful to demonstrate a lot of things. For example, any single object that's moving and ends up somewhere else in the end has a non-zero velocity. So let's do a quick example. Let's say we have a road, a straight road, and we have a car, and that car is traveling from the road. Let's say the road starts at x equals 0, and right now the car is at x equals 5. And the car keeps on going until it ends up at x equals 55. And it reaches that in a time of 10 seconds. So we know that delta t equals 10. Delta t equals 10 seconds. And we want to find the velocity, the average velocity the car has experienced going from x equals 5 to x equals 55. Now, recall, we know that velocity is delta x over delta t. So we would first write that equation down. V equals delta x over delta t. And we know delta t is 10 seconds. The car took 10 seconds to go from here to there. So we could just plug in our known value, 10, over here. But what is delta x? Well, delta x is a change in position from here to there. So it would just be final position minus initial position. 55 minus 5, that would be delta x. This is really simple stuff. And once you simplify it, you will get 50 over 10, which is just 5. And of course, there are units, but since the question didn't specify what unit it is, we don't know if it's meters, centimeters, so we're going to say 5 units per second. And that's how fast the car is going. And since it's on a 1D plane, there can only be two directions, positive and negative. Recall, velocity is a vector. Is a vector, which means it must have a direction along with the magnitude, which is 5. It must have a direction. So in this case, let's call this the negative direction and this the positive direction. Sorry. All right. So since it goes from here to here, it would be positive. So we could say for our direction specified 5 units per second, that's positive, so plus 5 units per second. Or you could say 5 units per second to the right in square brackets. And both of these ways work as long as you specify a direction, because you must have to include a direction for velocity. Now, what if the car was speeding up? When you are on a car and you're at a traffic light, your car doesn't just go from 0 velocity to 50 velocity, 50 miles per hour. It actually has to take some time to speed up, and that would be called acceleration. Well, what would acceleration be? Acceleration is the change in velocity over time. Over change in time. For example, if you go from 0 miles per hour to 50 miles per hour in a span of 10 seconds, your acceleration would be 5 miles per hour squared. But we'll get into the units later. So this is change in velocity over change in time. And we can actually modify this equation to help us solve more complex questions. And in most problems, we would use this. So we know the formula for velocity is delta x over delta t. So if you sub that in to v, sub delta v equals delta x over delta t, you would get something like delta x over delta t over delta t. And when you go to it and you simplify, your final form of acceleration would be delta x over delta t squared. The change in distance over the change in time squared. So now this might sound a bit confusing, so let's do an example. Let's say a car, again, this example, oops. In this car, starts at rest. At rest means its velocity is 0 at x equals 1. And after it starts from rest, it constantly accelerates up till x equals 51. And when it is at x equals 51, it's took him, let's say, 10 seconds to get here. So it started at rest at x equals 1, and it took 10 seconds to get to x equals 51. And you're asked to find the average acceleration of the car. Well, you see the original formula. Acceleration is change in velocity over change in time. And although we could calculate for velocity using our formula above, delta x over delta t, it would be easier to just use the formula we derived here, which is change in distance over change in time squared. So acceleration, usually represented by a, would be just plug in the variables, change in x over change in time squared. What is change in x? Well, it's 51 minus 1 over change in time squared, which is 10 squared. And that would be equal to 50 over 100, which would be equal to 1 over 2 meters per second squared. And like like velocity and displacement, acceleration is a vector, so you will need to specify a direction. In this case, it's positive, so I'm going to write positive, but again, it's totally fine to just specify that it's going right, unless your question states otherwise. All right, so we know that this car is going at is was accelerating at 0.5 meters per second squared. Now, what if we had another scenario? What if we had the acceleration and we had the amount of time accelerated? Can we find the velocity it was at the end? Let's say on another example, this time the car went from x equals 90 to x equals 10. So the car went backwards. And it started from rest. So I hear v equals 0 meters per second. And it went all the way to x equals 10. And when it was at x equals 10, we want to know what its velocity is. So v equals what? Let's say it had a constant acceleration of negative 10 meters per second squared. Remember, it's negative because it's going to the left, so it's going in the other direction. So we just need to use some basic algebra to modify this equation. When we get into later kinematics, this algebra is going to come in really handy because we will be dealing with much more complicated equations. So we know that acceleration is delta v over delta t. Delta v over delta t. And we want to know delta v. We have delta t. Sorry, we can calculate for delta t. So, yeah, acceleration equals delta v over delta t, but we don't know delta t. How can we calculate delta t? Well, we can use this formula. Acceleration equals delta x over delta t squared. So, I would first go and calculate delta t. let me just erase this. So when calculating for delta t, we use that formula again. A equals delta x over delta t squared. We know the acceleration is negative 10 meters per second. Delta x is just the final position minus the initial position, which is 10 minus 90 over delta t squared. And when you simplify, you get negative 80 over negative 10, which is negative 8. Positive 8. So delta t squared equals 8. So t would be equal to either 2 root 2 or t equals negative 2 root 2. But this is inadmissible because you cannot have a negative time. Alright, so we know that t is 2 root 2 seconds. And now you have t, so you can calculate the actual acceleration. So we'll go here and we'll rewrite a equals delta v over delta t. And we know acceleration, negative 10, equals delta v is just final. Let's call this v final, v of f, minus initial, which is 0. So vf minus 0 over delta t, which is, we already calculated this, 2 root 2. So in general, v of f is negative 10 times 2 root 2, and that would be equal to negative 20 root 2. And I would not leave it in a radical. I would expand it and round it to your set amount of sig figs. The number of sig figs really depend on what course you're doing. For example, AP, usually it depends on the question, but usually 2 to 3 sig figs. So 20 root 2 is about 28.28. So I would do negative 28.2 meters per second, or 28.2 meters per second left. And that would be how you calculate velocity with the acceleration and the change in distance. And that's all for 1D motion analysis. So basically what we learned is we learned some equations, for example, the change in distance, the change in displacement, and how to calculate for velocity and acceleration in many different problems that we can use very efficiently. And we will be using a lot of these problems, a lot of these equations in the future. Thank you for listening.